Welcome to the next module on control unit. So, in the course, in the last module, we have basically seen that what is the basic architecture of a computing system, like we have a control unit, then we on the other side we have the memory, we may have some peripherals, and then at a very theoretical level we have seen what are the components inside, like a memory block, then we have also seen what are the registers inside a control unit, then we have seen an ALU, how they are connected, and also we have seen a very theoretical notion that how a code gets executed. But you might have thought that such a complicated situation that a instruction is taken, then just the next instruction is taken after that, it is decoded, fetched, and so many integrated steps happen. And they also happen in the hardware where everything is in terms of bits. So, that means there should be lot of control signals, or there should be lot of control intricacies which happens which helps for a code to execute in such a integrated environment, that is on a basic computing system. So, the last module was on the basic architecture of that system. In the next module, that is on the control unit, what we are going to see? We are going to look at basically how those units, like for example your registers, your memory, your CPU, your buses, how they are basically interconnected, and what are the signals and what are the exact signal flows that is required, and how the signals are generated so that a code executes in a correct fashion. So, in this module we will be mainly concentrating on how a control unit is generated, what are the required signals, how the signals are generated, and how the sequence of signals actually maintains a proper flow of the code execution. So, that is the basic idea of this module. So, in this module basically you will be mainly looking at the instruction cycle and the micro operations inside that. Then we will be mainly looking at control signals and timing sequence and so forth. So, you can go through all the different units in this module. So, this will give you a feel that basically this module focuses on what are the instructions, how they are divided into micro instructions, and how automatically some control signals are generated which actually are required for the control flow of the data in the registers or CPU buses, etc., and how basically what are the different ways of actually generating the signals in the control unit. So, a code executes in a code and the interrupts, and if you have a, for example, jump instruction. So, how basically a code executes, and what are the required control signals for this generation, and how actually timing is organized, and what are the timing issues, etc., which we will be learning in different units of the module. So, the details of the modules are available in this slide. So, as we are going by a pedagogical aspect, so let us discuss on the module summary, that what is going to be covered in this module. So, in fact, as we already discussed in the last module, that basically a computing element has CPU, ALU, special purpose registers, instruction registers, etc. And basically there are several ways to interconnect them, that whether you have a single bus architecture, whether you have a double bus architecture, whether you have 3 bus architecture, whether you have some local memory for a local CPU, etc. So, we will study in this module how basically different ways of connecting the components, like as I told you about 2 bus, 3 bus and 3 bus organization. So, we will have a look at this, look at the idea of such interconnects of such units like registers, CPU, etc., and then we will see for different such configurations how are signal generated and how actually the flow of code moves, because it is very obvious that if you have 3 bus system, the execution of code will be faster compared to a single bus system, because if a single bus system is there, then there should be lot of multiplexing, because there is a one resource which is a bus and it is only dependent on for all data transfers. But for example, if you have a 3 bus system, then actually some bus can be dedicated for register to register flow, some bus can be used for memory to register flow and so forth. So, therefore, the control signals will also be different in the latter case compared to the former case. If it is a 3 bus system, the code execution will be faster because you have now 3 buses to solve the problem and so forth. So, we will be looking at how control signals are generated and in different processor organization configurations. Then basically, as I told you, whatever your code moves and how a code is sequenced, or if I say that you fetch a code or fetch a instruction or you fetch a data, that means some signals has to be generated. Like we have already seen that if you are looking for a memory, you should generate whether it is a read write signal, we have to generate some values for the memory buffer register, and when the memory buffer register has already or the data is already given to the memory buffer register from the memory, you should generate a signal saying that the data is now ready and it has been sent to the buffer, you can read it. For example, you want to write something to the memory, then you write it into the memory buffer register and then you have to wait for some time. All these handshaking signals, like for example, if there is 0 flag, so So, the 0 flag is set, that means a control signal will be generated. So, all such different signals, how they are generated and how they actually involve in the flow of code or flow of code execution in the control unit will be studied. Then we will actually see different functional arithmetic logic units in terms of different control signals. In other words, here in this module, if you compare to the previous module, we will look at the same thing, but in the last module we assume that data is fetched, then if there is a control instruction and the flag registers are set, accordingly program counter will change. But here we will deal with how they change and actually what are the control signals that result in the change and how those control signals are generated. Like for example, as I told you, if there is some flags, so flags are set and reset, they generate some control signals. How those control signals will be utilized and how you can design a circuit which will read the control signals from the wire and modify the program counter. Now we will be looking in a much more hardware related issues than a superficial level which we will last look in the last module. Like for example, the output of the control units determines the signals which actually are subdued to another function module. Like for example, there is a peripheral device. So, the peripheral device will interrupt your system. So, if it is interrupted, what type of control signals will be generated? So, in a nutshell we look at different type of control signals, how they are generated, and we look it for different architectures like single bus, multiple double bus and 3 bus architecture. Then basically another very important thing is that whenever we will be talking about the control signals, we have to first understand that like a very simple instruction which you have already seen in the last module, like add a comma p or add a comma 3030 hex, that is the memory location. So, in fact this is something called a macro instruction, but a macro instruction will also involve some kind of micro instructions. Like when we say add a comma 3030 hex, that means first there should be a micro instruction which will be involving to read the data from the memory location 3030 to the memory, to the accumulator, or in this case register A or whatever may be the instruction like. So, in fact that will involve some kind of micro operations or micro instructions, like first you have to give the address of 3030 to the memory address register. Then you have to wait for certain amount of time when the memory will generate a signal that data has been given to the memory buffer register from 3030. So, that is a control signal which has to be read from the memory saying that data from 3030 location has been given to the memory buffer register. Now, your instruction register or your accumulator will read the data from the memory buffer register. So, these small steps, like then obviously after instruction is executed you have to increment the value of PC. So, a larger instruction like add a comma 3030 involves several micro instructions, as I told you, incrementing the PC, writing the value of the address in the memory address register, reading from the memory buffer register. After the signal, the memory gives a signal that I have written the data. So, all these small instructions we call as micro instructions, and we assume that each micro instruction can be operated at 1 unit of time. So, basically in this module a substantial part will cover that are given a macro instruction, or in other words an instruction like load, add, subtract, multiply. What are the micro instructions involved in it? What are the different micro instructions for a macro instructions? How they are sequenced? How they can be optimized? And how basically we can write for a given code? How can we write it in terms of micro instructions? Or how basically, and in fact you might have observed, as I was telling you, that for each micro instruction some kind of control signals are generated. Then we will see that basically for a given code what are the micro instructions, and then we will study basically how we can generate those micro instructions. So, micro instructions basically there are two approaches, one is called the hardware approach and one is called the micro programmed approach, which basically generates the control signals depending on your micro instructions. So, in this module we will be looking at depth in both the ways. So, in a hardware control based micro instruction or control signal generation means we will have a finite state machine which is a hard coded machine which is implemented in the hardware, and based on your micro instructions or the micro instructions correspond to the main instructions, your flow will move in this sequential machine, because we know that it is a sequential operation. So, a sequential state machine will move and each state will generate the control signals, and we call it as a hardware business because it is fixed to the hardware and you cannot do any changes there. But of course, a more flexible version of this is called microprogrammed environment. So, in microprogram environment you can assume that basically it is same thing like a normal code involved, but in this case your micro instructions will not be hardware like a hardware control, but you will have another simplified set of codes for each macro code, or in fact for a given instruction which I am for the time being calling macro instructions, it will involve some kind of micro instructions. So, micro instructions will be very similar to a normal set of instructions, and but instead of a program counter which is involved for the macro instructions, here there will be something called the MPC, which is called the micro program control construction unit. Main memory, it will be a separate memory for these micro instructions, or in other words, in case of microprogrammed based unit, you can assume it that for each macro instruction there is a simple code corresponding to the micro instructions, and it will also execute in sequence like the macro instructions, but instead of large instructions like add a comma b, here we will have small instructions like load memory address register from the instruction register, load the value from the memory to the memory buffer register and read the signal. That means now the instructions are at the micro level, which can be executed at each time unit. But you can think it like macro instruction 1, 2, 3, 4. Each macro instruction will lead to some micro instructions. It will also be stored in a microprogram memory. It will also have movement like 1, 2, 3, 4, and instead of the program counter, here we will have the microprogram environment. So it is more flexible. So more details will come up when we will reach the absolute exact modules we will reach through. So now if you look at it, what are the objectives of this module? So the objective of the module, first is a comprehensive objective. You will be able to describe about the control steps and control signals needed to execute an instruction. This is one of the most important part of this module. That we will give an instruction, sometimes I will call it macro instruction to differentiate it from the micro instruction. So if I give you an instruction like I say that load accumulator 3030. So you will be able to tell me what are the exact control steps and what are the exact control sequence required to do it. Then is a synthesis objective. So synthesis objective says that design issues of control steps of the basic instructions like read memory for execution which refers to a given organization. That means you will be able to design a system or a computing control unit system with given to a given organization. That means if it is a single bus or multiple bus, then you will be able to design the control steps required. You can also design the micro instructions and the control signals required to be generated. It can be a microprogram control, it can be a hardware control. So you will be able to design such a system based on a given organization. Of course, you will be also able to design, that is another synthesis objective, design instruction for control operations like branch, function call, etc. So in fact, I mean the two design, here we have separated out the two synthesis objectives. One is for the normal arithmetic data transfer operations and the another set for branch instruction, interrupt instruction and call return instructions. Then of course, two important things, you will be able to design this control signal based on hardware based control unit and micro program based control unit, that is the hardware business as well as software business. And the last instruction is again a design instruction. So you design issues for implementation of the micro program as well as your hardware control unit. You will be able to design both, compare among them both and find out which is a more optimized implementation at any point of time. So this is actually the main module objectives. Now look at the module learning strategy. So basically unit 1 and unit 2 will be basics of this module, where we will study the instruction cycle and the micro operations of an unit. Basically in first unit we will be learning that what is an instruction cycle, that we know fetch, decode, execute, sometimes we have an interrupt and so forth, and what are the micro instructions available for them. And the second one basically we will deal with the timing sequence, that exactly what is the time cycles and more integrated details of the control signals will be studied over there. So first unit will tell what are the signals, the second unit will tell what are the exactly timing sequence in terms of timing diagrams. Unit 3 will describe the control signals and timing sequence required for a complete execution of a continuous instruction. In 1 or 2 we will be building the basics, and in third unit we will take a large code and we will take an organization like a single bus, multiple bus, and we will see how it goes. Instruction 4 and 5 will take different addressing modes and we will study the same thing. Like we have already seen different type of instruction modes are available, or sorry, different type of addressing modes are available like direct, indirect, base, displacement. So we will see how the control signal generation changes whenever there are different type of addressing modes. Instruction 6 will describe about the hardware control unit. So, now in instruction 6 we will deal with that if you are given a set of instructions, if you want to make a hardware control unit, how to design that. Unit 7 will tell you about the different type of bus architecture. Basically, as I was telling, that we will study with in depth of different type of single bus, multiple bus, and we will study for all of them how to design the control set instructions. And last 2 units will basically deal with how to design microprogram control units for different bus organizations. Basically, that is what is the idea. So, initially we will start with very basic instruction set, what are the micro instructions for that, then we will look at the timing sequence, then we will see if for different set of instructions or different addressing modes how they change, then we will give you an idea of hardware control based design, and then we will also give you an idea for how to design a microprogram control based unit for generating different type of signals and control signals in a control unit, and also we will look at different architectures in terms of different bus system buses, single and multiple. So, basically I am not going to read out this slide, you can look at it. We are describing here basically what are the different units and from which book you can study this. Basically, we are referring William Stallings book and Hamacher's book. So, exactly which unit, which topic and which module you have to read, like for example, unit 1 which chapter you have to read are all detailed down in this slides basically. So, I am just keeping this slide for a few minutes, you can look through it. Also, you can go for this NPTEL based course, which is a web course on computer organization architecture. You can go through this in this way, you go to the module on CPU design. So, basically this gives an overview on a very pedagogical sense that what is the objective of the module on control unit, what is the basic summary of the unit, what module and the units, what we are going to expect out of that, and what are the objectives you are going to meet after this module is completed. Now, we are going to go for the first unit. So, as we have told you that in the first unit is a very basic unit. In this case, we will just look at different macro instructions. In fact, instructions, again I am terming them as macro instructions because I want to differentiate them from the micro instructions. So, in this case, we will see a instruction cycle which you are always saying fetch, decode, execute, store, and sometimes there may be an interrupt. And what are the micro instructions involved for each of the instructions. That is what is the first unit on. That is, we are going to see basically given a macro instruction, how it can be divided into micro instruction, and as already told you, micro instructions basically are the atomic instructions which execute in a single clock unit and which totally comprise a generic instruction. So, this is the first module, that is instruction cycle and micro operations. So, in this unit as a pedagogical sense, what we are mainly going to look at this unit. So, as I told you, machine instructions are generally complex and require multiple clock cycles to complete. That is, as I told you, if you have an indirect machine instruction, that is add indirect a 3030. That means the location of the variable which has to be added with 3a is not available at 3030. At memory location 3030, you will find another address and you have to go to that address, there they will get the actual value which has to be added with a. So, it is indirect mode of addressing. So, and if I have something like add a 30 immediate. So, of course, you can understand that the immediate mode of instruction or immediate addressing mode will be extremely fast compared to the indirect mode. So, it says that all the instructions are of different complexity and they will take multiple clocks to execute. So, basically what happens? So, each instruction basically has to be divided into some kind of atomic instructions or micro instructions that can be implemented in a clock cycle. That is what will be the main emphasis of this unit, in which case we will take different instructions and we will tell you basically what are the micro instructions available for that. The operations involved in the 4 cycles can be carried out using 1 or 4 micro operations in some predefined frequency. Like basically, I mean generally 4 cycles, as I already told you, fetch, decode, execute and store. So, basically what happens? Fetch, we already know that. So, first is the fetch the contents of the memory and load them to a CPU register. Store the word of a data from a CPU register to a given memory location, that is your load store instruction. Transfer a data from CPU register to another CPU, perform arithmetic operation and store the result in a CPU register. So, you can see that there are different types of, these are data transfer operation and actually there is one arithmetic operation. So, if you think about, most of the instructions can be predefined in such kind of a thing. You load from memory location, store to a memory location, transfer data in between different registers of the CPU and or you perform the arithmetic and logic operation, and we first store it in the register and then we can write it in the CPU. So, basically these 4 are in a nutshell or in a very broad terms can be classified as different type of data movements in a control unit. So, if I can generate some micro instructions for this given broad flavor of data movement, that will actually give you a very good idea that how a macro instruction can be divided into micro instructions, because as I told you, memory to memory operation directly we do not support. We take a data from the memory to a register and then we can again write it back after doing some logical operation. So, in more or less these 4 types give you a basic idea, and for this type of 4 basic idea we will try to see what are the different type of micro instructions. So, as I told you in a very simple nutshell, because nowadays processors are more complicated, you can have different type, means clock frequency, means some of the micro instructions will take 2 clocks, some will take 1 clock. So, all these complications are there, but for the time being we are taking a very simple controller design because it is the UG first level course or architecture. So, we will assume that micro operations are such operation which can be done in 1 clock pulse. More or less even in very sophisticated architectures also, generally 1 micro instruction means 1 unit of time, but some variations happen. So, that is what is the idea. We will take a very simple control design which is this one, which is simple thing. However, there may be micro operation involving data, movement of data in or out of the registers, they do not interfere with another. We will see that basically what idea is there. In that case what it says, what we will study in this case, there is something called optimization. Like for example, 1 micro instruction, you are reading some data from the memory to a register, but at the same time your CPU is doing some computation and writing register to another register 2 say, and you want to at the same time you want to read something from a memory location to register X. So, they are non-conflicting instruction. So, you can actually merge these 2 instructions at one time unit. That means, they are all micro instructions, they will take one, but you need not sequence them because they are non-interfering. So, if you give directly separate time units to all this, then you require more number of micro instructions to operate a macro instruction. So, what we can do is that we can optimize and try to put in parallel or in one time unit some of the micro instructions which do not require a separation in time gap. But if for example, as we will see, if there is some dependence on the first micro instruction on the other, then we cannot put in a single time go. So, basically also one important idea is that we assume that all the micro instructions take single unit of time, that is fine, but depending on the instructions, if they are non-dependent instructions, we can put them in one time go, which is actually which is actually called clock grouping. The term is called clock grouping, that you put 2 instructions which are non-dependent on one another, you put in the same time unit, so that there is optimization in time. So, we actually call it as a clock grouping. So, we will also see that given a macro instructions, one of the micro instructions, and we assume that each micro instructions take 1 unit of time, then we will see if there is some non-dependent micro instruction, then we will try to put in one time unit, and we will see what are the minimum number of time units required to execute a macro instruction, which is actually called clock grouping, and it actually optimizes on the time. So, what are the unit objectives? In this unit objective, the first objective is a comprehension objective, which you will be able to discuss the concept of instruction cycles, macro operations of an instructions, the micro operations involved in a macro operation. That is the first objective of this unit, that given any macro instruction, you will be able to tell what are the micro instructions of that. Also specify the different phases involved in an instruction and the micro operation needed out to carry those phases. Like as I told you, that if I say that load X or load accumulator 30-30. There are certain steps, like for example, the instruction has to be taken from the memory to the instruction register via memory buffer register, then 30-30 will be loaded from the instruction register to the memory address register, then the memory will give the data from the 30-30 memory location to the memory buffer register, which will be again read back to the accumulator. So, there are different stages. So, we will discuss the different stages, you will be able to specify the different stages required to execute a macro instruction in terms of micro instructions. And finally, is a design objective. Given any instruction set, you will be able to design the micro instruction required to execute the macro operation. So, again now we are coming to the module. So, what is a micro instruction? Machine's instructions are generally complex and require multiple cycles to complete. So, machine instructions are also termed as macro instructions in this context. So, as I was telling from the very beginning, that if you are taking a large instruction, like say I was reading say add accumulator, I am writing across specifically, then I call 30-30. So, in this case, as I told you, it is a macro instruction. So, add A is the accumulator from 3030 memory location. So, you can assume that if it is a direct instruction, time taken will be certain. If 3030 is not a memory location, but if it is a immediate data, then it will be extremely fast. And if 3030 add, this add is a indirect instruction, that means first you have to go to memory location 3030, there is another instruction over here, you have to go to another part of the memory and then you will get the data. So, memory instructions are very complex depending on the addressing mode and what it operates on, etc. So, basically we divide it into granular level, which is called the micro instruction, and each micro instructions can execute in a single time unit. Taking multiple micro instructions, you go for a macro instruction. That is what is told in the second point, that basically it says that each machine instruction is implemented in terms of micro instructions, data flows and controls that can be executed in a single clock pulse. That is, if I want to get a data from a memory to the memory buffer register, we generally assume that the clock duration is such, because generally in a simple terms memory reads and writes are done in a single clock pulse. So, we actually design our clock in such a fashion, or we limit our speed in such a fashion that most of the micro instructions are executed in a single clock pulse. And that is, if you are not able to do it that fast, you have to actually relax the clock period. So, in that case the frequency of the processor will come down. If you have very fast memory, you have very fast interfaces, multiple buses, then many of these micro instructions can be executed in less amount of time. If that can be done, then you can reduce the time period and you can say that the processor is a faster. Okay. And in other words, micro operations are detailed lower level atomic instructions which can be executed in a single clock and are generally used to implement complex machine instructions. That means you join the micro instructions and make a macro instruction, or whenever you are designing a macro instruction, you have to go for in between, you have to go in delay in the leaf level, there will be micro instructions. So, micro instructions I told you different classes: register transfer, arithmetic micro operations, logic and shift. Basically that I told you, that is the data transfer and basically your logic transfer. Mainly these are the broad classes. So, what is there? You have this is a very nice figure which actually shows you, gives a description that what is a micro operation. It is a program which will have lot of codes like load, store, add, multiply, etc. So, it has around n instruction. So, each instruction, as you can see, can be divided into fetch, decode, indirect and execute. That means sometimes the indirect may not be there for different addressing modes. Then fetch, that means some instruction has to be fetched from the memory to the instruction register. So, it will involve some micro operations. Then interrupt, it will involve some kind of micro instructions like a fetch. So, what are the different type of micro instructions? If you can think in such a manner, fetch means first the program counter will have the address of that memory from where the data will be loaded. Data will come from the memory to memory buffer register, from the memory buffer register it will go to the accumulator, certain steps are there. Then basically the program counter will be implemented. So, these are some of the micro instructions which is required in fetch. Decode means what? There will be a hardware which will actually read this opcode from the instruction and generate certain signals. In this module, we will be mainly looking at how signals are generated for an instruction. Like for example, if the opcode is 001, maybe 001 stands for load. So, the hardware will generate the signals corresponding to the load after reading this opcode of the instruction. So, that is again will be the decode part. So, again after reading the load part, again you have to do something, you have to take the instruction from the instruction register, you have to take the instruction, look at the other part of the instruction that will have the data address like 3030. So, you have to take that and then that will again go to the memory buffer register, memory address register, again the data will be fetched. So, lot of small integrated atomic details are required when a instruction is fetched, the instruction is executed. Like instruction has some stage like fetch, decode, indirect, execute or interrupt, and each stage also has different atomic level. So, they are now actually the micro instructions, and this one will take 1 unit of time, this one will take 1 unit of time and so forth. So, again the number of micro instructions for a given instruction depends on the instruction type. So, for a simple instruction the number of micro instructions will be less, for a complex instruction the number of micro instructions will be larger, but each micro instruction is taking place at a single clock period of time. So, it is a very nice and a synchronized way of handling the system. Now, we will take different examples of micro operations and see how it requires. So, for example, we are going to take a fetch subcycle. So, we are going to take fetch, decode, indirect, execute, interrupt. So, many subs are there, we will take one at a time. So, let us take fetch, that means memory is there and this is what is the instruction. This has to be fetched to the instruction register. That is what is the fetch. That means, the program counter basically already has given the value in the memory address register. The memory address register, now it has, the memory address register has to be given the value of the PC. Now the program counter value is already telling that this is the address of the memory where the instruction is there. It will send it to the instruction, but not directly basically, as you already know that there is something called memory buffer register. So, memory will give the data from this from this location to the memory buffer register. Memory buffer register will send it to the instruction register, and you have to increment the PC. So, these are some of the micro stage of operations which are required to do it. So, what at the first time unit what will happen? The program counter will load the memory address register. That is, program counter PC value is there. It is telling that that is your memory address register. The program counter is telling that this is the location from where I need the instruction. Then this part is done. Then what we will do? Now this memory will put this data to the memory buffer register. That is the second stage, second unit of time, that the memory will put the data in the memory buffer register. Now what? Now you have to increment the value of program counter, because next instruction has to be fetched in the next cycle, and then the memory buffer register will write it to the instruction register. So, you can see that I am having 4 basically micro instructions, and they involved in the fetch instruction. So, all these program counter value to memory address register, memory buffer, memory to the memory buffer register, program counter incrementing, memory buffer register to the incrementing to the instruction register, they all take some single unit of clock, and these 4 steps or micro instructions generally correspond to the correspond to the fetch subcycle of the macro instruction, which may be something like add a comma b, because all instructions will have these 4 subcycles or 4 or 5 cycles, like fetch, decode, execute, in between you may have an indirect, and towards the end you may have indirect. So, if you look at this table, so many micro instructions will be leveled out for an instruction. At present we have looked what are the micro instructions for the fetch part. Now, the concept of clock grouping is coming. So, each macro instruction involves a sequence of micro instructions. If you want to keep it very simple, just you take a flat implementation, means whatever is the macro instruction then is there, what are the stages you have, fetch, decode, indirect, execute, interrupt, divide it into the micro instructions and take that much amount of time. But you will find out that we always do not require to sequentialize it, because some of the 2 instructions, micro instructions can be done at a time. In that case, you can save some unit of time. So, if you can parallelize that, that is actually called clock grouping, like in this. So, in this fetch time, so PC is equal to, we are keeping the value of the memory address register. Can I actually merge these 2 in a single time take? Not possible, because in the first unit, the value of the program counter will go to the memory address register. You give some time, you give 1 unit of time for that. Then the memory address register will be read. Now, the memory will know that I have to supply the data, which is actually the instruction, from the address which is given in the memory address register. So, if I merge these 2 together, there will be a lot of hodgepodge, because you tell me that I have to deliver from this address and deliver it now. How can I do that? I require some time to read the address, go to the relevant location, bring the data and give it to you. So, I cannot merge T1 and T2 at a single point of time. But if you look at it, I am giving some, because this job is over. You have told me what is the address. Now, I go and bring the data from that memory location. Already you have given me from where I have to fetch the data. Then the job of the program counter is over, because program counter is telling me the address from where I have to get the data from. So, you have told me the address, and now I am going to get the data from the memory. Now, the program counter is free. So, better you can increment the program counter. So, it is very obvious that I can merge step 2 and 3 together, because after reading the value of the program counter to the memory address register, my job is done. I am free at hand. So, if you are free at hand, then actually I can reuse the PC, that in this case I am incrementing it by 1. So, taking the data from the memory to the memory buffer register and program counter increment, these 2 micro instructions you can do it in time steps 2, because they are 2 non-dependent micro instructions. Of course, the last is memory buffer register, we will be writing it to the instruction register. Of course, PCU can be merged with T2, PC increment can also be merged with T4. So, anyway you can merge. Of course, again I cannot merge steps 2 and step 4, because step 2 actually tells that I am bringing the data from the location. Before the data is brought to the memory buffer register, you cannot directly transfer it to the IR. So, these 2 are memory interdependent instructions, and 2 and 4 are interdependent instructions. So, they cannot be merged, but this one is an independent instruction, even these two are dependent. So, you can either merge it with this or you can merge it with this. So, basically 3 time steps or micro instructions are required, or 4 micro instructions are required, but in 3 time steps you can complete the fetch stage. That is what is said is called a clock grouping, that I am grouping. So, that I am grouping basically these 2 guys together, or I can merge these 2 guys together. So, 4 micro instructions, but I can do it in 3 time steps. So, what is clock grouping? Proper sequence should be maintained. You cannot alter the sequence. That is, I am getting the data before I put the registers in the address. That cannot be done. Proper sequence should be follows. Ideally, there should not be any conflicts. That is, there cannot be any biasness. I mean, so there cannot be any what do I call race condition kind or a actually conflict of interest kind of a thing. That is, I want to read from that register, at the same time you cannot write to the register. Those instructions are called conflicting instructions because they are using a common resource either for read and write. So, you cannot do at the same time, and program counter is always involving an increment. So, you try to feed the program counter at some place after the data is being read, or after the instruction has been read, then the program counter is free. You can try to increment the program counter and try to feed it in some place where there is no conflict. So, that is how basically the ideas of clock grouping is very simple. Sequence you cannot change, you cannot have any conflict. Like if I want to read from register R1, you cannot put a micro instruction at that same level in which it is updating it. Similarly, we have given an example, but program counter is bit free, because whenever the program counter has given the data to the memory address register to fetch the instruction is free, you can use it and put it in parallel. Again, we will now see the stage we already discussed, we are discussing for the fetch. So, first stage is program counter value to the memory address register, memory buffer register will take the value from the memory, you can merge these two, and the memory buffer register will write to the instruction. This is very simple. That is, for example, if you have an instruction say add accumulator 30 immediate. For such an instruction this is very simple. First you will fetch it, then actually maybe from this program counter will give the value in the memory address register. So, in that memory address let us say that this instruction is there. So, PC will be incremented and then the instruction register will have this part. Now, you want to actually execute this. Then exactly what happens basically, depending on whether 30 is an immediate or 30 is a memory location, the number of instructions in the decode phase will change. That is we are going to look at it. So, in the third stage it says that the memory buffer register will write to the instruction register. So, if it is an immediate data, more or less our job is done, because now your instruction register basically has the memory buffer register which is having the data called add accumulator 30 hex, which is an maybe immediate. In case of immediate, you did not do anything, because once the memory buffer register has dumped the value in the instruction register, you have already faced that maybe this add is add immediate, the opcode corresponds to immediate. So, you can directly take it and there is no further micro instructions required. But assume that in this case it is an indirect or it can be a direct, but it is a non-immediate mode of addressing. Then in this case what happens? Say it is, let us take add accumulator 30 hex. So, it is a direct addressing mode. So, we are saying that take the value from the memory location 30 hex, you go to the memory location called 30, whatever data is there you add it to the accumulator and store it. So, in this case what happens? This one will come to the accumulator. So, this whole thing is now. So, this instruction or the value of 30 is now in the instruction register. But now what happened? You have to now again give this value of 30 to again to the memory address register, because this is say some location called say 6. See, program counter value was 6. So, program memory location 6 had this instruction. So, it is now in the instruction register. But now again you have to now load the memory address register with this 30. Then again you have to read the value of memory location 30 to the memory buffer register, and only that will be again brought into the instruction register, and then again you can add it. That means a two-stage process. Immediate means you can directly whatever is in the memory buffer register, like we have seen add accumulator 30, you can directly take in the memory buffer register, go to the instruction register, add it and you are done. There is no further more step required. But if it is an indirect mode or a direct mode, but non immediate, that is data is not available in the instruction itself, then you have to go for multiple stages. Like instruction register address, you have to again feed it to the memory address register, that is this 3030, again I have to feed it to the memory address register. Next, memory buffer register, memory will write to that. For example, in 3030 we have the value called 6. That means we are going to add the value 6 to A and store it back to the accumulator. That is memory location 3030, let us assume that has the value 6. So, in step 3 basically you are going to read the value of add AA 3030 hex in the instruction register. Now, instruction register will know that again I have to go for its indirect, so it is a basically direct addressing, but a non-immediate addressing. So, it will again load the value of 3030 in the memory buffer register. So, memory buffer register, memory address register will have the value now 3030, and now the memory buffer register, the memory address register will take the value of 3030 from the instruction register. Memory buffer register will take the value from the memory location 3030 and put it to the memory buffer register, and then this memory buffer register, which is having the value of 6 now, will be loaded to the instruction register. So, now the instruction register will have add A 6. So, it will load it to the accumulator after adding. So, in fact, now some more instructions are required, like in this case this will be required, which will solve the problem. But again you see, none of the instructions can be put in one time step, because in this case you are reading in time T3, you are reading the instruction register address, that is 3030 in the memory buffer register. You have to give some time, then only the memory address register will be read, and you are going to give the value in the memory buffer register. After some time, the memory buffer register address, that is the data from that address, that is 6, will be loaded to the instruction register. So, in fact, you cannot parallelize, because this one is dependent on this and this one is dependent on this. So, you cannot save any time step in that. So, only time step which we save is that is in time step 2, we have merged the memory buffer register writing from the memory, and we have add program counter. So, what we have seen, so if it is a simple immediate mode of addressing, then we require 3 steps, 1, 2 and 3. That is, in step 1, this can be considered step 2 and this can be considered step 3, and if it is a non-immediate mode, that is maybe a direct mode. For indirect mode, maybe several other steps will be required, because more complicated your instruction is, more number of micro instructions will be required. So, in case of a direct, we need another 3. So, total number of stages, time steps will be 5. So, what I was telling you is that we are writing in this slide that what are the dependency, like for example, memory to memory buffer register and instruction register to the memory. We cannot put these 2 micro instructions together, because first the memory value will go to the memory buffer register, after some time from the memory buffer register it will go to instruction register. You cannot merge these 2. So, you have to have a proper sequencing. So, what we have seen, if you are not going for any clock grouping, then the number of time units required to go for a fetch immediate instruction will be 4, and if you optimize it, 1 will be saved, that is the incrementing of the PC will be saved, and you require 3. Similarly, if this is a non-immediate mode like a direct mode of instruction, so it is either 5 or 6, because we are optimizing the program counter increment, which can be fit with any other stage. Before we end, some other micro operations for different other stages of instruction I am showing over here. Say for example, this is for the interrupt cycle. So, if there is an interrupt instruction is there, what are the micro instructions? So, in the beginning we all know that the micro instruction, whenever there is interrupt, you have to save the value of program counter, and whenever the interrupt service routine has been done, you have to again come back and pop up the value of program counter and restart from where we have left. So, obviously we have to store the value of the program counter value somewhere. So, you write the value of program counter in the memory buffer register. Please note that we are not writing the program counter in the memory address register. Program counter writing in the memory address register means you are fetching some instruction. Here we are writing the value of program counter to the memory buffer register, because we are saving the value of PC. So, saving the value of PC means the value of PC I am writing to memory buffer register. From memory buffer register, it will basically go to a place where it will be saved. Now, where I have to save it in the memory, that will be actually the address to save the PC content. That is actually a stack address where we save the value of program counter, some temporary registers before the interrupt service routine is started. So, you actually in the what you do, so you can see that first stage I write the value of the program counter in the memory buffer register, second stage I write in the memory address register to save the value of the program counter. So, now basically already in the first stage you have saved the value of your program counter in the memory buffer register. Now I give the address where you have to save the value of the program counter in the memory. But at the first stage PC is now free, because already you have saved the value of PC in memory buffer register, and after that you are going to give the address in the memory address register where the value of MBR has to be saved, and indirectly the PC will be saved, but in the first stage only the PC has saved. So in time 2 you can put the PC to the starting address of the interrupt service routine. You do not require a T3 over here. T1 you save the PC in the memory buffer register. Step 2 you write the address in the memory buffer register, sorry, memory address register where you want to store the value of PC. At the same time you increment the value of PC because PC is free. So in this case you jump to the interrupt of service routine, and then in the time step 3 the memory buffer register will write the value to the memory whose address was given in the memory buffer memory address register. So in step 3 actually you are physically saving the value of the program counter. So instead of 4 you can save it in 3 time units. Basically we have merged, because of clock grouping we could merge the memory address register writing and the program counter increment, because already we have saved the value of program counter. And the simple, this was all about basically load, store, fetch and some kind of interrupt type of a part of the macro routine. But now let us take a very simple instruction like add Rx. Basically that is, you want to add the value of R, some memory location, and memory location is X, content of X you want to add with R and save it in register R. So basically what are the micro instructions involved for this? Fetch already we have seen, maybe it has been fetched etc. Then what is the case? So basically this is already in the instruction register because we assume that it has been fetched. So from the instruction register you have to get the value of X, sorry. You have to address X means the value of X, that is 3030 in the example we are looking at it. So memory address register will be fed with the value of address of X. Now the memory buffer register after some amount of time we load the value that is of 3030 assuming that is X, the value in the memory location X which you are calling as 3030 in the example, that value in that location will be loaded to the memory buffer register in time 2, and the time 3 basically which is the logic operation, the accumulator, sorry, the means arithmetic and logic unit will be involved, it will add the value of memory buffer register with the register R and it will be saving it in R. So this add Rx will be done in 3 micro instructions. And of course you can find out that there is a lot of interdependence because neither you can parallelize, means you cannot put memory this first instruction with second and second with third. So they are all interdependent instructions. So 3 instructions are required for that. So basically in this unit what we have seen, in this unit basically we have got an idea that there are macro instructions and each macro instructions must be implemented in terms of some lower level instructions which are we calling as micro instructions. And how micro instructions basically together are responsible for implementing a macro instruction, and each micro instructions are so finite or so atomic we need not break it down into further level. Basically each micro instruction involves some kind of control signals which will actually make them operate, that we are going to see in the future units to be coming. But macro instructions, micro instructions at the modular at the unit level or the atomic level together they make the macro instructions and a code executes. For each micro instructions we will see that there are some kind of signals which are generated. We will see in the future units how to generate these signals and how basically they involve in real hardware to execute, like if I say add, how the corresponding micro instruction, what are the signals it generates to exactly make it add the 2 operands by the CPU. Okay, so before we end, basically let us look at some of the questions. Like first question is, what is the micro instruction? Explain the principle of program instruction in terms of micro instructions and micro operations. And second instruction, if you look at it, this and these are the objectives, like discuss the concept of instruction cycle and micro instruction operation. So directly if you are able to answer this question, this instruction, this objective is satisfied. What is the concept of clock grouping? Like specify the different phases of involved in a micro instruction to carry out those phases, design the sequence of micro instructions to complete the instruction execution. So if you are able to specify and design, of course you will be able to optimize it in terms of clock grouping. Give the micro instructions involved in fetch instructions, give the micro instruction involved in the interrupt cycle and execute cycle. So these questions basically, these are questions for assignment. When you will be solving these questions basically you are easily going to satisfy these objectives. Like the first one is basic concept of micro instructions. Third and fourth questions basically tells you about different phases of the instructions and basically what are the micro instructions involved in it. So basically these questions actually satisfy this objective. So, after solving, after discussing this unit, you should be able to solve the questions and hence satisfy the objective. And whenever we are going to try to optimize the sequence, then the concept of block grouping is coming. So, basically with this we come to end of the first unit. From the second unit onwards, basically we will be more specifically looking into the control signals which are generated by each of the micro instructions, which exactly or accurately result in the flow of the code. Thank you.